These are trying times for everybody, and I'm sure we have a lot of questions, such as will I be able to continue my physics education? Does Mr. Stellato live in a classroom? Or will this allow me to see his adorable dog, Jimmy? And the answer to all three questions is, in fact, yes. Come here, buddy. Jimmy is here to say hello. Oh, Jimmy, go look at the camera. Oh my god. Jim, come here. Come on. Oh, he's very happy to see everybody. He's very excited. He'll be joining us today. Come on. And this is Jimmy, everybody. Say hello. Say hello. Jimmy, being rude. He's a sweet boy. So, what we are going to focus on today is the relationship between circuits, work, power, and energy. And we've started talking about circuits already. We've been working on them for the last week or so here. So we're going to expand out why these things actually matter in your day-to-day life. So, let's take a look at some of the equation work that we have done so far. We talked about how voltage is equal to work divided by charge. We talked about how current is equal to charge per unit time. And in the past, we did how power is in fact work over time. We're going to blend that with V equals IR in a second, but I want to write out a simple equation first here. Let's imagine if we multiply voltage by current. Voltage times current. Let's look at what actually happens here when we break this down. Well, if you rewrite voltage, and we can rewrite voltage here as work over charge. And remember, work, same thing as energy. It's work or energy, both measured in joules. And current is charge per unit time, charge per second. Well, if we multiply these by each other, work per charge per time, let's look at what happens with charge. We notice that charge cancels out, and we get work or energy divided by time. Well, what is work divided by time? It's something we've worked with in the past. It's power. So when you talk about electrical power, which is measured in watts, it's the work per unit time. It is your voltage, or your potential difference, times your current. So this brings us to another fundamental equation, a very important equation in physics, and that is power is equal to voltage times current. P equals VI. Power is equal to voltage times current. We can use that to solve simple problems that involve this. If, for example, we had a simple circuit, and this circuit has, let's say, a 12-volt battery, and this is what a battery will look like, and we'll talk about that more soon, a 12-volt battery, and let's say it has a charge of 3 amps, or 3 amperes, not a charge, sorry, a current of 3 amperes and a voltage of 12 volts, well, you could find the power in that circuit. We have a voltage of 12 volts times a current of 3 amps, and that would give us 36 units of power, and our unit of power, of course, is a watt. We would have 36 watts of power. Jimmy's had enough. 36 watts of power here. And we've probably seen that used with light bulbs, with electrical circuits involved in anything in our house. So we can see that power ties into all this, and we see how this is kind of blending back into some of the stuff we already worked on this year. Now, if you take power, you can multiply it by something else, and it will give you work or energy. What you multiply by is time, because power is work over time, power times time is work. So we could say, well, power times time is work. So if we want to find the work or the energy in a system like this, work or energy, it's going to be V times I times time. Potential difference times current times time. So let's say we took the same circuit and we operated for 5 seconds. Well, how much energy would it use? You'd simply multiply this by 5 seconds, and you would get 180 joules of work or of energy. We want to remember energy and work are the same thing here. That's our intro to it. P equals VI, very important equation, similar to V equals IR, and now we're actually going to combine them together. So P equals VI, and we all see that, it's not too bad. Let's combine this with our other equation, V equals IR. Well, P equals VI, and V equals IR, so you could replace V here with IR. And that would give you I times R times I. Or another way of saying it, power could be I squared times R. Current squared times resistance also gives you power. Another way you could say it, well, I here, current, is equal to V divided by R. And if the current is V over R, and we're multiplying that by voltage again to get power, well then power is V squared over R. Potential difference squared divided by resistance. And any of those times time will give you the energy in the system. This is all written very clearly on your reference table, in fact, and we can take a look at how they write it out. We're on page 4 here, just below all of the equations we have worked with so far. So if we look here on page 4, it says power is VI, I squared R, or V squared over R, and work, power times time, is VIT, I squared R times T, or V squared T over R. So we should start seeing a connection here between our circuits and their relationship to power, energy, watts, joules, and we see the cycle kind of repeat here. Jimmy, you want to sign off? Say goodbye, buddy. Say goodbye. Say goodbye. That is it for our first virtual lesson. Thanks for watching. Please get ready for our first teleconference. We're going to have those a little bit later this week. I believe Wednesday for 10-2 and Thursday for 10-1. Those times are posted on the Harbor. Try out the worksheets, check the answers, come to our digital conference with any questions. But now we have 2 big picture equations we want to remember. P equals VI, V equals IR, and all of this, of course, is on your reference table. Stay healthy.